All right, this is one of two titration problems, number 13 here. In one experiment, 100 mLs of 0.1 molar nitric acid is titrated with 0.100 molar sodium hydroxide. And then you're asked to calculate the pH of the solution at different points along the way. Okay, so we want to go through and systematically think about one thing that's going to change during this titration is the amount of HCl as we add sodium hydroxide. Some of the HCl is going to react and it's going to disappear. The other thing, though, that's changing is the total volume. So at the beginning, before we've added any sodium hydroxide, we just have nitric acid sitting in the flask with a concentration of 0.100 molar. All right, so for A, let's write that down. We have 100 ml of nitric acid with a concentration of 0.100 molar. Okay, and so if we wanted to go ahead and calculate the concentration, the moles at this point, we could. I mean, we might as well. We'll need it here in a second. So I'm going to convert my milliliters to liters by dividing by 1,000 and then multiply by that concentration. Okay, 0.01 mole of nitric acid. But we didn't really need that to figure out this first pH. So pH is equal to minus log H3O plus. And in this case, we know basically the amount of H3O plus. It's 0.1 molar. And so minus log of 0.1 means the pH at this point is exactly 1 before we've added any base to that solution. B, okay, so 0.0100 moles of nitric acid is what the flask started out with, and we've added in some base. So 25 out of 1,000, again just converting the milliliters to liters. And that base also has a concentration of 0.1. So that gives me 0.0025 moles of sodium hydroxide. Well, so exactly 25% of that nitric acid is going to get chewed up. So at the end of the day, we're left over with 0.0075 moles of HNO3, and it's currently in 125 milliliters. I'm going to go ahead and make that into liters because I'm going to need a concentration again. Concentration of H3O plus 0.0075 moles in 0.175 liters. Excuse me, there on the bottom. Okay, 0.06 molar is the concentration of H3O plus. So now I'm going to go minus log of that, and so the pH at this point is equal to 1.22. Okay, I had this much acid, I added that much base. The base chewed up 25% of the acid, and this acid now is in a larger volume. It went from being in 100 mLs to being in 125. I took the amount of acid that's left over, divided by the volume of the solution, get the molarity, and then I did minus log of this concentration to get the pH. Right. These next three are going to be very similar to this. So again, if we started out with 0.0100 moles of nitric acid, and Then we had 50 mLs of base. At the end of the day, that would leave 0.0050 moles of our nitric acid. But now in 150 milliliters, or 0.150 liters. It's getting neutralized and diluted. Okay, 0.033 molar. Minus log of that number. Okay, and what we like to see, the pH is getting higher. We're adding base. That makes sense. We're using up acid. And so the pH continues to get higher. Okay, now we're up to 0.0075 moles of sodium hydroxide when we've added 75 mLs. And now we're going to chew up 3/4 of what's in there. Okay, we're only going to be left with 25% of the acid at the end. And it's in an even bigger volume. 175 milliliters or 0.175 liters. .014 molar minus log of that answer. pH equals 1.85. Okay, pH continues to rise. And then here in this last one, it's going to be a little weird. So this is how much acid we had in at the beginning. Now our base, have 100 mLs of the base, up 1,000, up 0.1. Lost a 0 there. Okay, the number of moles of the acid and the base are the same, so there's no concentration of HCl, or there's no excess concentration of sodium hydroxide. What does this mean? This means it's a neutral solution, and there's not a calculation you need to do here. You just need to know at neutralization conditions, the pH is 7.